Namaste. Working? Good. Konnichiwa. Okay. So now I turn it to a little bit new subject, which is application of cluster algebra structure or cluster pattern structure. Namely, the subject is called Dilogarithm identity. It's a fascinating subject. Have a lot of history and okay. So anyhow, I give some few background. So according to the point of view of cluster algebra, our history is divided at 2000, you know. And before that, it is called before cluster algebra, back in BC, and after that, it's, you know, 80. Okay, anyhow, the history of Dilogarithm is much longer, starting by Leonhard Euler, but especially my subject started around 1980s, and it happened in the context of mathematical physics. Mathematical physics. As a keyword of this area is, I just mentioned some keyword, Yang-Baxter equation, Bethe ansatz, and also what is called conformal field theory, often written as CFT. Anyhow, there are various things found, proposed, and conjectured. That is, first of all, I mentioned yesterday briefly, but periodicity property, periodicity of various Y systems, which I don't write it, but it is some function and have some nice functional relations called Y system. And the solution of it automatically has a periodicity is a conjecture. And also is somehow very closely related there is a Dilogarithm identity, which I will explain soon. But it is an identity satisfied by a single function called Dilogarithm function. Yeah, and those are all for simplest case, some simple case it is proved, but generally proposed as a conjecture. Yeah. And in a BC, I mean before cluster algebra, people of course try to prove this conjecture. It looks statement is simple, so many people try to prove it, but so sooner or later, including myself, we found that there is no way. It looks like there is no way to prove them. And somehow people stop to try to prove it. Then after that, you know, and in this stage, there is no concept of cluster algebra at all. And then cluster algebra was introduced around 2000. And somehow, gradually, people recognize that as this Y system is actually a part of this cluster algebra pattern, which I briefly explained just by speaking a little. And also, after that, including myself, I recognize that we recognize that this diagram's identity is also a part of business in cluster algebra. And we can summarize this statement in a following simple way. Suppose you have some periodicity. happen in cluster algebra. I mean, the periodicity of mutation in cluster pattern. Yeah? I explained it yesterday. Then there is an associated Dilogarithm identity. Is a general theorem. So I repeat, for each periodicity in cluster algebra, there is associated Dilogarithm identity, is a statement. And today I explain this very basic theorem. And then we apply this to each cases and showing the periodicity of Y system. And then this conjecture Dilogarithm is automatically obtained as associated Dilogarithm identity. So these conjectures are proved. So now we see a nice history of mathematics that without this concept, there's nothing really. It's like a perpendicular wall, which there is no way to have anything which you can put anything. But you know, there is a way, stairways from the behind, and you can just climbing up without any difficulty. And that stairs was a cluster algebra. So I'm going to explain this fascinating subject. Yes, and so Dilogarithm is a quite analytic function of single variables. So it is considered as a part of analysis, of a subject of the analysis. And history go back to Euler. And I'm actually going to introduce two kinds of Dilogarithm. So we have two S, and first one is called Euler Dilogarithm. Dilogarithm. Yeah, so this is the original one. And so, you know, Euler is in 18th century. Anyway, nowadays it is written in the following notation. I will explain it very soon. So, but it is called Li2 Ax, Li or Ax. Okay. So first of all, it is just defined by the following power series along the x equals 0 origin point. Yeah. And so this 2 is 2, and you can replace it to 1 or 2 or 3 or 4. And when it is 1, basically it is a logarithm function. It's just power series expansion. So it is, and so 2, it is called Dilogarithm. And if it is 3, it is a trilogarithm. And higher one generally called polylogarithm. Yeah? And especially this Dilogarithm is quite concerned in the business of cluster algebra. And this power series has a convergence ratio of 1, so it defines a function, analytic function on the complex plane. Yes, and you can have as following integral expression very easily. It's a good exercise, so you just expand the log in a power series expansion. And then just formally integrate this one, and you end up with this one. Or you can differentiate this one, then and differentiate this one, and you obtain the power series expansion with this one. And once you have this integral expression, then you can analytically continue this function to hold the complex plane. However, there is a caution, because we have log function in an integrand. There is a branch. So by analytical expansion, it defines a multivariate function on complex plane. And to avoid this ambiguity of multivariateness, we somehow, in our purpose, it's enough to concentrate on. So branch actually have 2.1, and after that, actually, with multivariateness of this log function, 0 also becomes a branch point. But anyhow, if you concentrate on this real integral, you just think that this is a real integral, then everything is well defined. Okay, so we somehow limit ourselves on this function for my purpose. Yeah. For other purpose, it's necessary to consider as a complex function. Anyhow, I'll give you two important property of this function, which is obvious. The first one is obvious. So when you put 0, because this is 0. Yeah. But this property is very much important. And second important property, I mean, this constant value 1 is a very special value. So if you put it 1 as an bit, becomes a z function, yeah? And at the point 2. Yeah? So this function is a z function, or Riemann z function. And this value itself was proved by Euler that it becomes a famous value, yes, pi square 6. And these two numbers are very much important. And so if you say plot this function using, say, for example, mathematical, it is a built-in function in mathematicals, and so value is, say, here is pi square over 6. Yeah. Then a function somehow looks like the following. The graph is something like this. And it will go diverges. Yeah. And it's a monotonically increasing function. Yeah. So there is nothing special for this graph, but the speciality of this function is written as follows. So it satisfies various functional identity. And example will be given very soon. So anyway, so that those things I call a Dilogarithm identity. Because it's a wrong word, I somehow simply said it DI. So Cluster Algebra CA and Dilogarithm identity DI. Yeah. I use this abbreviation a lot in my lecture. Now, before giving an example, I introduce the second variation of Dilogarithm. It is called Rogers Dilogarithm. And this Rogers is the famous Rogers of Rogers-Ramanujan identity. And it itself has already has a history of more than 100 years. And oh, by the way, I forgot to mention why it is called Li, because of this form it is considered as a logarithmic integral. Logarithmic integral. And Li stands for these things. Okay, so now Rogers Dilogarithm generally written as L, sometimes called Rogers L function, and it is defined by a kind of symmetrization of this integral expression of Dilogarithm. So the first factor is exactly the same one. And second factor is a kind of symmetric to make it symmetric to the in the following sense. And we divide by 1/2 to make it symmetric. And now this function, as a definition, this one, but also you can partially integrate this part, then you actually obtain this function, and this 1/2 is once again cancelled, and you come back to this one, and you can write. But we have some surface term coming from this partial integration, which is log x times log 1 minus x. Yeah. So up to this elementary function is essentially equal to the Dilogarithm function. So and you can see once again that this constant term, of course, by definition is 0. On the other hand, we have 1, and you use this property, and you put 1 here. Yeah, so we have Ly2 1, which we know the value, and here we have 0 times minus infinity, which to be 0 due to the log property. So in fact, the number is still the same. Yeah, so this factor is 0 at x equals 1. So, but now, not only obvious branch at x equals 1, here we have obvious branch at x equals 0. So, once again, this is a multivariate function, and if you consider this integral as an analytic continuation. And somehow, in my talk, it's enough to consider this in this region in a complex plane. Yeah, you can of course analytically continue to any other things, but especially we consider this real intervals. Yeah, and interesting things happen in this region. So let's try to plot a function here, x x. And also it is built-in function of mathematical, and you can see the result. So it's something like, and due to this symmetrization, it becomes symmetric with respect to the middle point. And it somehow looks like as follows. So it's something like this. Slightly curved and passing through the middle point and go to this. And so, but if you see really is a plot of mathematica, it's almost like a linear. But of course, it's not a linear. But it's almost like a linear. It almost looks like a linear monotonical increase function. It's once again, there's no special point which you can see in this graph. What is good about this function? I can tell you it simplifies many, probably not all, but many Dilogarithm identities. Yeah. So that's why Rogers introduced this function, probably I suspect. And now it's time to give an example to somehow explain the feeling of these things. And those two I'm going to explain is the most classic one. Most classic example. The first one is due to Euler. It is called Euler identity. It's a very simple identity using this Rogers Dilogarithm function. It is explained by this, where those x are in between 0 to 1. And before explaining anything else, let's prove this identity. It's very simple. The proof consists of two parts. So first, this identity means that the left-hand side does not depend on x. And especially this constant value is this one. And so first, let's show that this is constant. It means you just make a derivation of left-hand side. Then you see from this expression, you just get this function, which is symmetric to x and 1 minus x. But because of this minus sign, additional minus comes up in derivation. So they cancel. So this is 0. Yeah. So we need to next determine the constant value. To do that, because we know that this is a constant, we can evaluate it at some particular point. If you put x equals 0, let's use this fact. This sum is 0. So this is L1, so this is this one. So the value is this one. Yeah? So proved, yeah. So we don't need to Euler to prove this identity, of course. But anyway, this was first discovered by Euler as a, I mean, regarded, Euler pointed out that this is an important functional relation. Okay. Second example is due to Abel, so Abel identity, also known as pentagon identity. Yeah. And it is a kind of it is an extension of a generalization of this identity to two variables. So we have now not only one variable, but also other independent variable x, y. Yeah? And they specify the following relation. So we have 1 minus x of y. There are 5 terms. And the summation is a constant, and its constant term is, well, 3 times 6 pi square over 6. So this is, of course, this is, you can cancel in a bit too, but it's better to write this in this form. And once again, it is those x and y are anything in between 0 and y. Yeah? So it's a functional relation. Okay, let's prove it. Yeah. Once again, the strategy is the same. So you first make a derivation of this right-hand side, either this one and or this one, both becomes 0. Of course, it's not obvious as this one. It takes, I would say, 5 minutes if you are successful at the first time. But you know, there are a lot of minus sign and so on. So probably you make a mistake at the first moment. So, but still you can correct it, and after within 15 minutes you can prove it. Yeah. So this is left as the exercise. Yeah. So we know that this is a constant. And then once again, we need to determine this constant value. For that purpose, set x and y to be 0. Yeah? What are those variables? So they are 0, right? This is 0. What is this? This is 1. Yeah? This is 1. This is 1. 3, 1. Yeah? Means this 3 times of this value. And we can determine this one. Yeah? And by the way, this proof is really working for more general Dilogarithm identity. In fact, that is a strategy we prove these things. Yeah? So first show that the left-hand side is constant, then try to identify the right-hand side by setting some special value. Okay, now, very good. Now, I somehow a little bit reveal some advertisements also. First of all, so these two classic one is actually associated to the cluster algebra pattern of type A1 and A2 respectively. So yesterday, this you have this linking diagram to cluster algebra by Jacob, and so it turns out this identity is actually from general picture is associated to type A1 and A2. So you know it's a tip of iceberg, yeah? And there are much more general things behind it. Also, I want to mention a little about this pentagon identity because we are here in India. So you know this identity is much related to Ramanujan identity. So in Ramanujan identity, if you know, there's a number 5 is very important. Yeah, you consider some product modulo 5, and then this 5 is related to this number 5. And in fact, there are more cross relationships But I don't have time to explain it more detail. Anyhow, so these two are classic example, and it's already very, very good. So once again, to prove this, you don't need Abel, but you need Abel to discover this function. Yeah, and I'm going to say that the cluster algebra produce this kind of identity, infinitely many identity, and so it just corresponds to the periodicity of cluster algebra. Yeah. I don't know. I don't want to say that every dilogarithm identity obtained in this form. Yeah. I just say some dilogarithm identity is covered by cluster algebra structure. Now it's time to explain how they are more closely related. So cluster algebra and dilogarithm identity. Yeah. So first, I just recall. In my two lectures, what I have explained you, yeah, in a just very, very simple, short way. So to define a cluster pattern, you first fix a natural number called rank of a cluster pattern, and also P semifield. Yeah, and this is what is relevant to our problem is just the semifield of real positive numbers. Yeah. Yeah, that is very, very useful. Okay, so they are a semifield, and then we consider Y pattern, which is for each. Now you are familiar with this notation, but now for each vertex of n regular tree, you associate a Y seed, each are Y seed. Such that this has width coefficients in this special semifield R plus. So they are just positive real numbers. So what I mean is so this BT is a skew-symmetrizable integer matrix. Yeah, skew-symmetrizable integer matrix, and for later I want to use its skew-symmetrizer. So let me write with a skew-symmetrizer. Say D. Yeah, it's a diagonal positive integer matrix, which make these things to be skew-symmetric by left multiplication. Maybe I recall you everything. Okay. And also, I recall you what is YT. So YT is a n-tuple. Y variable here, Y variable all live in positive real numbers. Okay. Now, and they are related by mutations, right? So we have, if 2 points are connected, then this Y seed, mu k, which maybe this way, so D prime are written connected by the foreign mutation. Yeah, that is a Y pattern. Now, you know, I really don't want to repeat the expression again, so I somehow skip. This is something, and this is something. Probably for Y, maybe I just recall because it's nice to exercise to write it, then if you write it, say 100 times, you will remember it. Anyhow, oops, T prime. Sorry. Times y, kt, b, t, something, yeah? Now here, this is a plus of actually a semi-field, but we consider this a semi-field of a real positive number, so it's just simply an ordinary plus. There's no fancy tropical somewhere anything, yeah? So it's just, by this, it's a rational transformation of real numbers. Very good. And then I recall the following, because I want to formulate my Dilogarithm identity using a sigma periodicity. So I recall what is sigma, so it is a permutation. Of 1 to n. And I introduce a notation for action of this permutation to a seed, which create a new seed, say, such that this new is given by the action of sigma to the index, like this, yeah. It's the right action, but it's not important anyway. Something like that. Okay. So now everything is ready to state my theorem, Dilogarithm identity, which generalize this in a very drastic way. So suppose you have a sequence of mutation. Yeah, I use the same notation yesterday. Sequence. So sequence of mutation is considered as a discrete time dynamical system. So it's nice to consider it as there is a discrete time, and so I introduce this time zero as an initial things, and so those are some seed and then. Oh, probably I don't need to define this Y pattern, but we directly working on this sequence mutation. But anyway, so this is a mutation formula. But anyway, so first you choose your favorite direction is direction k0 at time 0, and you get something considered as a time 1 state. Yeah. And then you make a mutation to some other, or if you wish, k0 is the same, and whatever. And you repeat, say, t minus 1, t times, starting from 0, and you end up with something, yeah? Suppose this is the initial state, and this is the final state at time t, yeah? Let's call this sequence mutation as a star. And then the theorem, due to myself, Dilogarithm identity, it is as follows. So suppose that this sequence mutation is sigma periodic. Namely, it's the final state of the sequence of mutation is come back to the original one modulo this sigma permutation of indices. Yeah, simultaneous permutation of indices. Yeah, so this I call this sigma periodic. Then whatever this sequence is. As a statement, we have the following Dilogarithm identity, which I call this di. Yeah. it is a summation for each time. And this L, so we write something here, so put some space. And so L is a Rogers L functions, yeah, Rogers dilogarithm. And at each point, you pick up your y variable. It's now some real positive numbers at time t, but especially the component corresponding to the mutation direction, kt. Yeah. So at each point, you are going to mutate to some direction. And exactly at that point, we pick up like this. And we sum up, so it is some, so once you choose arbitrary choice of n tuple of positive real number, it gives you n tuple of real positive number respectively, and you can calculate this. And notice that if y is in between 0 to infinity, then those number itself is in 0 to 1. So Rogers L function is well defined exactly in this region. Yeah. So it's the value is in between 0 to 6 over pi square. It may be some most probably is some irrational number, and you sum up with weight d, k, t, where d is a component of skew-symmetrizer, but especially you pick up exactly the point for the direction of the mutation. And the statement is, so it's some number, so it's some positive real number, yeah? And is a constant with respect to the initial value of this your y variable. So this is constant. So it doesn't depend with respect to initial y values, yeah, initial values, yeah. So it's a functional relation, exactly the same sense. So you can pick up any numbers, and then others function of this one, and this means you don't this. Whole sum does not depend on these things. And once again, so the same thing. So we have n tuple of a real positive number, which you can choose arbitrarily, but then other numbers are determined. But summation of this is a constant. It is a functional identity, and this constant is actually a irrational number, but it has the following form. Just like those examples. And I'm going to explain later what this integer is. Yeah? We will determine it just in the same principle. But anyway, this is a Dilogarithm identity. Great. And I'm going to explain that for simplest two cases of type A1 and A2, this identity exactly reproduce this classic Dilogarithm identity. This is my main job today, to explain this. Okay. But before that, I give a kind of method of proofs. So there are several, and I by myself prove this statement in three different ways. So first method. There are many ways to do this. So this is due to myself, but the first proof was a purely algebraic method. Or maybe I would say cluster algebraic method. And to prove this identity, the principle is same. So you, like this, you want to first show that left-hand side does not depend on the initial value y0. And so it means you can take a differentiation of this to y. And then it has been known in 90s before cluster algebra introduced what kind of condition make this combination to be constant. It is called constancy condition. It is proved constancy condition due to Frenkel and Senesh constancy condition. And I don't write it explicitly, but it is expressed as a certain algebraic relation. And we can prove this algebraic relation using our separation formula, which I explained last time. Yeah, and so this is a kind of brute force. So constant condition shows that this one, left-hand side is 0. So this is a direct proof. I don't have time to explain this more detail, but second one is a kind of should proof. It is not not rigorous proof, but still illuminating proof. Rigorous. Yeah. Well, I would say mathematical physics proof. This was due to Kashaev and myself. Maybe something like this. I don't know. Actually, one can quantize this identity, and it is called quantum dilogarithm identity. So via quantization. And the corresponding identity was first formulated by Fock and Goncharov. So there is what is called quantum dilogarithm. And dilogarithm, and they satisfy a similar identity called quantum dilogarithm. So this is due to Fock and Goncharov. And it is a little bit surprising, but quantum case is easier. Because I can't explain it quite simply, but then Hamiltonian quantum this system is exactly given by a quantum dilogarithm, and identity is just the multiplication of this quantum dialog is a constant, which is obvious from the periodicity of corresponding quantum cluster algebra. So this one is easy consequence of the periodicity. So you can prove this easily. Now, I want to derive this identity from quantum one. That is not simple things. It is, you have to do this, what is called semi-classical analysis. Yeah? So semi-classical limit. Because everything here is not a number, quantum theory, it is operators, and here we have some numbers. So to get some numbers from operator, you have to do some analysis, so-called semi-classical limit, taking expectation value and so on, and taking the limit of say this Planck scale to go to 0, and you need to use some method called saddle point approximation. And that is very hard to prove general statement. And so that's that point, it is not. So we need to use this saddle point approximation. But it is a quite well accepted method in mathematical physics. And if you believe so, you obtain these things. So it's a formal proof. But still, it's nice that they are coming from this one by this limit. And third proof of this identity is, I like it best, I would say. So this is due to Gechtmann, myself, and Dylan Ruppel, more recently. we use a classical dynamical approach. Dynamical method. And I will explain this in the next lecture because I want to show it among them best. So I don't explain this today, but so tomorrow I will give a very simple proof of this statement using this approach. Then you really see what this identity really means in some this classical dynamical context. Okay, so let's postpone this, and I'm probably I can erase this, and I produce this quickly by this general theorem. Okay, so that's my main job today. So examples. I have 24 minutes now. So examples. First one, type A1 case. Type A1 case means rank is 1, and we have initial y seed, B of y, and for rank 1 case, it's a 1 by 1 skew symmetrizable matrix. There is no other choice that it is 0. Diagonal component is always 0. Yeah. So this is a unique rank 1 skew symmetrizable one, and y1 is there's one number which is real positive integer, arbitrary. Yeah. So this is our starting point. And what you can do? You can do only one possible direction of mutation to the direction 1. Yeah? And after mutation, this is still the same. So so this B is this B. Yeah? But why actually mutate? Mutate due to exactly these things. So y becomes its inverse. Yeah? So this is a mutation. Yeah? But once again, you have no choice, no other choice, but you have a mutation, and take an inverse of it, you get. Yeah? This is, of course, involution of mutation. But you can also interpret it as periodicity of length 2. Yeah? So this is exactly periodic with this sigma is now identity. So note that this theorem does not depend on the choice of sigma. Whatever sigma, it's okay. But in this case, exactly this is sigma equal. So it's really periodic. Okay, so let's write down the associated Dilogarithm identity according to this general formula. Yeah. So here D is just 1. You can choose it at 1, so you forget about it. So it is a summation of two things. First, you choose a mutation point, but you know there is only one choice. So this is exactly this one. Yeah. So this is the first term, and the second term we have this one. And okay, so I should write this more explicitly. I'm sorry. And the theorem says this is a constant, yeah. But in fact, this one multiplying y1 to numerator and denominator, you can write it as following way. Yeah? You just multiply this, then you put this x. If you add two of them, numerators now cancels. So it is 1 minus x, right? So this portion, if you add them, it becomes 1. So if it is, you set x, this is 1 minus x. And this x, if y1 take value from 0 to infinity, this value takes 0, not including this, but okay, so we have any number is taken, yeah? But, I'm sorry, so if it goes to infinity, it crosses to be 1, yeah, so because this one disappears. But of course, these are not taken, but by continuity. So once you have this functional equation by continuity, you can actually include the boundary. So this is exactly Euler identity, yeah, Euler identity. So that's why this Euler identity is associated to type A1 periodicity. Yes? I really can't hear you at all. Yeah. Theorem, yes? Oh, sorry, I made a mistake. Thank you very much. This is also T, yeah. So next, I want to make a type A2 calculation. It becomes a little bit longer, so I somehow erase these things. Well, it's unfortunate to probably I erase this portion and start to calculate from here. So now we consider rank 2, and we choose our initial B0, Y0 to be, just say set for simplicity B and Y, and B is as following skew-symmetric matrix. So the one corresponding type A2 in terms of quiver, it is to one direction. So this is type A2 quiver. Yeah, and it's a good exercise to fill up those things. So we have T, B, and Y. And at least you need 2 lines for each row of this diagram. So we have to, you need two rows to write down everything. Well, I screwed up a little bit. I somehow try to squeeze things here. Maybe possible. 1, 2, 3, 4. It's really very stupid. So let me write this a little bit once again. You need some strategy. Yeah, so first you write the middle one, and something like this. And I use pentagon thing. So from 0, 1, 2, 3, 4, 5, and after 5 steps, you get 6. No, 5. Why I'm so stupid? 1, 2, 3, 1, 2, 3. Okay, I have the, I don't need this. Huh? Okay, great. So each time I make a mutation, k of t is 1, 2, 1, 2, 1. So alternative mutation. And B matrix itself, starting from, so those are BT, Y of T, that I'm going to write. And yesterday, Jacob explained that if you make a mutation, it just go to the other direction. So in a matrix language, it becomes B. So it's just the matrix itself. Make an alternative or sign changes like this. And so there's a very small space, I'm sorry, but now this is an initial variable. And I first make a mutation for at 1, which makes these things y inverse. Probably it's a good idea to write in this way. So y1t, y2t, and y1. Okay, now I feel comfortable. And make a mutation at 1 indicated this line, because this information will be necessary later. Yeah. So this becomes y1 inverse. And according to that formula, which you can closely review later, but I give you an answer. So you have such a formula here. And the next time you're going to mutate at this point, and this one becomes just make an inverse. And this one is mutated more drastically. And after some calculation, you get this formula. Yeah, and so on. So you make a mutation to this one. You get y1. This is inverted, so y1, y plus 2 plus y1, y2 inverse. And this one becomes a little bit, sorry, okay, so sorry, this one, so this times 3, oh yes, so it becomes y1 inverse, y2 inverse, 1 plus y2, and so on, yeah. It's not a x variable, so it's not a Laurent polynomial anymore, but still have some simple form, yeah. And make a mutation here, you get y1, y2 is inverse. Meanwhile, this factor becomes much simpler. Like this point is something which you may want to closely check what's going on. Yeah? Anyhow, next mutation, it comes back, and this we have the final result. And this is tau 1 to periodic. Because those are interchanged, and also this is obtained as an interchange of simultaneous indices from this one. Okay, so this is a periodicity of y variable. Great, and we have mutated 1, 2, 3, 4, 5 times, and we have a 5 factor here. Oh, by the way, it's nice to mention that you see a separation formula clearly here. So this factor is actually the part where those power is given by C vectors. And sign coherence means it's always the same sign. So either positive or negative power. And the other term is coming from polynomial. But with some power, because for y variable, the non-tropical part has some power, overall power for f polynomial. So those are actually f polynomial. That's why you have the same formula, similar formula for x variable as well, as Jacob described it yesterday by calculating exchange graph. Okay, now everything is given, so let's just write down these things. Yeah. Okay. Then okay, it's actually it's your exercise, but a few times. So first, you need this one, right? Okay. Let's say. And the corresponding term here is just like this. And the second term, you have a little bit more complicated combination. 1, 2, 1, 1, 1, 2. And so on, yeah, and there are it's left for your exercise. So there are 2, 3, 4, and you just plug in those things into this. Yeah. It looks like complicated, but nevertheless, you just simply-mindedly set this is x, yeah, and this is y. And then once again, those numbers are in between 0 to 1 by the same reason as before. And for example, those things in Abel, so I do it in opposite way. So in Abel identity, for example, we had this term in the maybe fourth term of identity, and you can calculate these things. It's I did it myself. It's good exercise. So let's do it. It's just multiplication of this gives you some okay cancellation here. You know, it's not so obvious, but we have cancellation here. So we have this one, and this one can be written as using a common denominator, you can write this in the following way. It's not yet such a form, but you can divide this by common factor here. Then after that, these terms cancels, and you end up with this formula, which is exactly this one, yeah, because we have first term is given by this, and you plug in this, and you get this one. So it can be related as a more combination. But this one is exactly expected from Abel's identity. And there are two other terms which is left as a good exercise. Yeah, you just calculate these as a things. And it gives you this one, and the other term gives you this one, and so on. Yeah, it's a very good, nice thing. So conclusion. So they are exactly Abel's identity. Okay, so I'm going to finish today's. So proof will be given tomorrow. And I finished explain give some remark for this identity. So first of all, just by saying to apply this theorem, you need to prove some periodicity, and there we can use this tropicalization method yesterday. So to prove some desired periodicity, you can prove instead of this messy y variable, you do it in tropical setting. Of course, this method gives you how to prove periodicity, but it doesn't give you how to find a periodicity. And this is still an open question. How many? Yes, this is. Yeah. Yes, yes, yes. Yeah, yeah. Well, if you clever enough, you can do it, but it used to be a very difficult problem. Yeah. So the problem is, given a diagonal identity, can you find a cluster algebra periodicity? Is a good question, but the probably general answer is probably no. But I know, I don't know. Nobody knows. Yeah. Anyhow, back to the remark. Then the second remark is there is a quantization of these things which I have already remarked. So you can replace this quantum, this ordinary y seed to what is called quantum y seed, which now becomes non-commutative variables, and still the theorem is this non-commutative variables share exactly the same classical y variables. So they share the same periodicity. And then there is an associated quantum dilogarithm identity where you replace this function to, for example, Faddeev with a quantum dilogarithm function, and the summation becomes product. But I don't write it, it's explicit form. And but final remark is I'd like to explain the constant term. Here, we can easily see what should be in the following manner. So I say my claim is this dilogarithm, left-hand side dilogarithm, something like this. I wrote it there. Let me say, write it again. dkt 1 plus ykt t ykt t. This is our canonical form. Is some integer, and this integer is described in the following way. So to describe this integer, I recall you that in a first example, how we exactly calculate these things by considering the particular set your x and, for example, Abel case, you set x and y to be 0. And you calculate, so sometimes it becomes 0, sometimes it becomes 1. And you just count what term becomes 1. Is the number 3 in the Abel case. And we can do this principle. So, namely, you just set your initial variable. It is a kind of a free variable to be 0. Yeah. So, all initial value set to 0. Then, other variables, usually it's a rational function of such things. But you see, there is now, we can see now sign coherent property that all are either positive or negative. So it becomes, other terms goes to 1. So this one becomes 0 or infinity. No, if it is mixed, then I don't know. This is always a 0 or infinity, depending on a choice of how you go infinity of this one. But we have no concern because of the sign coherence. So sign coherence really knows this, responsible for this identity. So what I said is, this one, if say t is a sign, a tropical sign, of your mutated y variables with respect to the initial point t equals 0. Yeah, and then you can calculate the C matrix, and this is exactly the sign. this depending on your sign, if this is plus, then it goes to 0 because it goes to 0. On the other hand, if it is minus sign, it goes to plus infinity. Yeah, due to this singularity. Yes, and so now we know by setting this we have two things only, becomes 0 or 1. Yeah, because this 0 infinity means this combination becomes okay. I'm going to finish. Yeah, so 0 and 1, and 1 is coming from this one. So this is exactly the number of T such that corresponding tropical sign is minus. So that's why I put minus. Yeah. So this is a constant term. Yeah. Okay, I finished. Thank you very much.